The topic, as you can see, is fast radio bursts and extreme magnetism. And I can describe the first slide that I have. So I made a little list of things that we understand. Things like stars, we know what they are. They're basically balls of gas, and we know why they shine. There are thermonuclear reactions. Then, we have things like quasars. We know these are creating active galactic nuclei, creating black holes. We know pulsars. Their radio emission is produced by electron-positron discharge. We have things like gamma ray bursts, where we have jets and shocks producing emission. So we have a good picture for this main phenomenon that we see in the sky. Fast radio bursts should be added to this list as remarkable phenomenon for which we still don't have an established model. We think the sources are magnetized, maybe not for all of them. The mechanism of emission is not quite settled. Then what are the main questions that appear there? Of course, what's the emission mechanism? And another important physics question is how the waves propagate, what happens with these fast radio bursts on the way between between the source and us. So let's see. Actually, I think it's still downloaded. Okay, it's downloaded. Almost. Yeah, I can see it without my glasses. Okay, it's almost. So I'll go to next slide then. And the next slide, I think I remember it. Yeah, thank you. Okay. That's fantastic. Well, it was pretty close. Okay, that was first slide. Okay. Now, this is a very useful slide because it introduces what fast radio bursts are in terms of electromagnetism. They are very strong waves. And this is the strength parameter of the wave, A0, which tells you the momentum of a test particle that it would develop in the wave. Well, nothing works today for me, so I don't have a pointer, I think, but it's okay. Thank you. Yeah. This is frequency of the wave. This is amplitude of the wave. So if you know luminosity, then you also know the strength parameter. So the interesting aspect of FRBs, if they're indeed emitted by magnetars and they come from small radii, then their A0 parameter is huge. That means that the test particle will develop ultra-relativistic motion in this wave. Okay, so one thing you want to understand is how the wave could possibly propagate in the surrounding of the magnetar. This is showing the field structure around the magnetar. There is also, of course, some plasma, but there is very little plasma because magnetic energy density strongly dominates over plasma rest mass. This is very strongly magnetized plasma. There is dipole field rotating with the star, and there is a wind zone. Okay, so the first problem I would like to look at, and our tool set for today would be very modest. So we'll have a wave and an electron. And so I'm going to, and that's it, electromagnetic field and an electron. And these kind of problems are supposed to be solved, 100 years ago or more. All you need, of course, also special relativity and the discovery of the electron. And Thomson solved this problem for Thomson scattering after the discovery of the electron almost immediately. Interestingly, for strong fields, this is still an unsolved problem. I mean, now I think it's solved. I tried to describe the solution. I guess there was not enough motivation. So to look at this basic problem for strong fields. So I guess thank you, extreme electrodynamics of compact objects. So what is the basic problem? This is the Thomson scattering, right? So you have electromagnetic wave shaking the electron, and as a result, the electron emits, and the ratio of the emitted power to the flux, energy flux in the wave is the cross-section. Of course, it's easy to calculate this motion of the electron. We know we love this classical problem. It gives us the Thomson cross-section. Of course, it describes important phenomena in the universe, radiative transfer in ionized gas, in all context, radiation pressure in the Eddington limit, cosmic microwave background scattering. So one approximation here, of course, is that when we calculate the motion of the electron, we neglect the Lorentz force. So we assume that B is much smaller, of the wave is much smaller than, the V over C is Lorentz force, V times B is much smaller than electric field. That corresponds to a node parameter, which I just showed, to be much smaller than 1. Now, what happens when it's not much smaller, but much larger than 1? So this is still a textbook problem. It was, you can find it, for example, in Landau and Lifshitz. So, of course, how you solve it? You just write down the equation of motion. Now, you don't assume that beta V over C is small. The calculation is still the same for the cross-section. You still have this main parameter A naught, which now can be larger than 1. You can calculate the motion of the electron. Landau and Lifshitz do that using Hamilton-Jacobi theory. I'll tell you the shortcut. You can solve this problem in your head, basically. How you just need to extend a little bit the problem. So instead of focusing on solving an electron in a given wave, actually think about what the wave is doing. Okay, it's a test particle problem, but electron, of course, will gain energy from the wave and momentum from the wave. So the wave, whenever it loses some energy delta E, it will also lose some momentum delta P. And the difference, this quantity delta Q, is not lost by the wave because of the wave has relation between energy and momentum in this wave. We're talking about just plain parallel wave propagating. So if the wave doesn't lose this delta Q, particle doesn't gain this delta Q, and delta Q is energy minus momentum along the wave propagation direction, and you immediately get an integral of motion. And that's it, you are done, because this is for the Z component of motion. For the X component of motion, the problem is symmetric, plane wave propagating along Z. X and Y are invariant directions. And so you have conservation of generalized momentum, Ux plus potential of the wave, which of course is related to this A parameter. It's just E naught over C omega. It's just the A naught amplitude of the vector potential for the wave. For the Y, you don't excite the Y motion because there's no component of the A potential on the Y motion. That's it. You found all three components of Ux, Uy, Uz. You know gamma. That's the solution. You solve it immediately. 1 plus A squared over 2. So the electron oscillates with this amplitude. Gamma gets up to A naught squared over 2. Now, when you calculate the cross-section, it's easy to show that the power that you emit is proportional to this quantity squared. And so because the wave doesn't pass that quantity, the cross-section doesn't change from Thomson cross-section. So if the wave even a very strong wave, actually scatters electron with the same cross-section sigma Thomson. So what's happening, electron is going to be accelerated, keeps oscillating, and it has average motion with Lorentz factor of A naught, approximately equal to A naught, and it has similar oscillation amplitude. Okay, this is a classical problem. It's got popular, of course, for laser physics, because in lasers now have reached A naught much greater than 1. Now, what wasn't solved, and what is relevant for FRBs, is the same problem, but now you have the background magnetic field, and you want to find the cross-section for scattering. Now, of course, you have this additional parameter. Now you've got magnetic field, and it's still electromagnetic field, electron in the field, the wave is propagating. You want to know the motion of the electron, and you want to find the power that it emits to find the cross-section of scattering. In addition to A naught, you have now this ratio, synchrotron frequency over the frequency of the wave. That's one extra parameter of the problem. Otherwise, it's very similar. You just write down the equation of motion for the electron. You have the background. You can solve it. Okay, so I solved it. And the solution is actually quite nice. So first of all, we can observe that background field is important when, of course, it's strong enough. So what is strong enough? It's greater than this omega b in terms of cyclone frequency is greater than a naught strength parameter times duration of the pulse we're talking about to the -1. Its meaning is very simple. If your electron is moving, your pulse is long enough, the background field will turn around the electron. And if it turns around before the pulse is gone, you basically effectively magnetize the particle in the wave. So it's not now streaming with the wave, but it's gyrating in the wave in the background field. Okay, what does it mean for cross-section? Well, this is a summary of what cross-section does. This is the solution. When you have, this result was known before, when the magnetic field is stronger than B greater than A naught, basically means that the background field is stronger than the amplitude of the wave. And in that case, the cross-section is suppressed. Around neutron stars, this is a huge parameter B, if we talk about radio waves. And so there is a huge suppression by a factor of millions or a billion as a result of that. But in the region where electric field amplitude is larger than the background field, your cross-section is increased by a factor of a billion rather than suppressed by a factor of a billion. And the reason is that the particle becomes unmagnetized, and now it develops interesting motion in the field of the wave, especially in this regime. So what's happening in this regime? So first of all, the particle begins to move with huge amplitude A naught, interestingly with the same A naught that you find for the unmagnetized problem. But when you have, when you're in this regime, it's not only that. It's not only electron does not only oscillate with large energy in the wave, its motion also becomes stochastic. And then here is just explicit solution for one realization of this stochastic behavior of the electron. You start with the electron, give it a little kick initially in some non-zero temperature, whatever, to see the stochasticity, and let it go. Then you find that the electron will develop, and in general, that's the behavior of the electron in the wave. The electron oscillates in the wave, and it gyrates in the background field. And its motion just superposition of the two. You can see here what happens. The electron motion becomes stochastic in this regime. This is the regime when the background field, omega b, cyclone frequency is greater than the frequency of the wave. So in that regime, you develop strong gyration, and the amplitude of your gyration motion is larger in terms of energy than the oscillation of the wave. And every time you do a gyration cycle, you experience a resonance. So this resonance happens every gyration cycle. So this is your gyration. Gamma is oscillating in the wave. Then it comes to the moment when the electron is moving in the same direction as the wave is propagating, and it experiences the electric field of the wave for a long time, and that's the resonance, where there is energy exchange. So every Larmor rotation period, there is a resonance that boosts the electron energy in a random direction, because the phase of the wave that happens at that resonance is random. The oscillation is very fast, and therefore every Larmor rotation, electron effectively comes to the resonance with a random phase with the wave, and it can be plus or minus gain in energy. So you can solve this problem completely analytically, and of course you can solve it numerically. And like I said, should have been done 100 years ago. This is the solution for the mean expectation. On a computer, you would just run whatever 10 to the 4 realizations, and it's all confirmed. So you know everything about the behavior of the Lorentz factor in the wave. Then you know how much electron radiates, and then you know the cross-section is the result I showed on the previous slide. Okay, then there is a second. Of course, this motion continues. It's a very fast process, by the way, if you look at it, because this is a huge thing. And then, of course, this acceleration of the electron in the wave continues until the moment when it starts to lose energy with the same rate that it is gaining from the wave. And that's it. Then you have a steady state. And then in this steady state, the energy that you emitted, the power that you emitted divided by the flux of the wave is your cross-section of scattering. And it's a huge cross-section. All right, so another part of the problem, and this is new stuff that I didn't talk, I think, about before. I'll publish a paper soon on that. So it's propagation, second part of propagation problem that deals with radiation pressure, which is, of course, important and well known for the Eddington limit, for example. So what's the standard way of thinking about it? Okay, you have a pulse of radiation, And it comes to some plasma, and it's some duration. Okay, what is the momentum that you transfer into the medium? It's the flux, it's the cross-section, and if you use the cross-section that I just explained how you calculated the scales will A naught, you find that if you're thinking about something explaining radially, the total momentum you transfer goes as 1 over r to the 4th. So this is a standard picture. When you know the scattering cross-section, you know how you push the plasma. Because of the huge cross-section, you can push it very strongly. Okay, one little addition to this problem here, because the medium around Newton star is so strongly dominated by magnetic field that sigma parameter, this magnetization parameter, is huge. That means that effective inertia of the particle is not given by its rest mass in this problem, but it's actually dominated by the background field that is like a ballast attached to that particle essentially. The magnetic field is frozen in the plasma. And therefore, in order to accelerate the particle, you need the transferred momentum to be not greater than mc to accelerate at relativistic speed, but to be greater than a much bigger value, 1 plus sigma times mc. Okay, but once you have that condition, and you can easily have it around Newton stars, you have very strong acceleration of particles. One thing to observe, though, unlike normal canonical radiation pressure problem, strong waves can actually accelerate particles even without this effect of scattering. Scattering is attached to energy losses of the particle. So scattering cross-section is the ratio of emitted power to the flux, energy flux in the wave. Suppose this power is 0. Usually, okay, scattering momentum is 0. But in fact, in this case, for strong waves, because the wave, by accelerating particles so much, deposits energy in the plasma, with it also comes the momentum. Energy, when it loses energy, it also loses the momentum, like the argument I showed before, right? So even when you don't have radiative losses, you have a strong push. Okay, so now, as you can see, it is something to understand here. And this is, it turns out, difficult problem. There was a recent paper by Emanuele. I mean, he was one brave person. I mean, not many people working on this, remarkably, because it's tough, I guess. So Emanuele's result for the problem was the following. So you have this pulse, it goes into static MHD fluid. If you have non-radiative push, just forget about radiative losses for simplicity. And what he finds is that the drift speed is that the plasma is pushed to the drift for velocity equal approximately to A naught parameter. That is huge for FRBs because A naught is so large. Okay, so this calculation was done assuming a steady state, meaning that you have steady propagations, like steady front propagating through the plasma, and regular oscillations in the wave. Regular meaning the wave, this regular oscillation are two regimes. When omega b is greater than omega, you have the stochastic interaction with the wave. Omega b is smaller than omega, you have regular interaction. So the corresponding compression factor in the packet, that what they find is 1 plus A naught squared. Huge effect because A naught is big. So this cannot be right. And it's easy to see why it's not right, okay? Because it's independent of sigma. And if you take limit of very high sigma, when you use a lot of ballast and magnetic energy attached to the particle, basically go to the vacuum limit. If you gradually remove the plasma from the picture, of course, the wave that goes through the background field is not going to push it. So this result is independent of background field, and it's got to depend on it. Okay, and so how do you solve it then? And of course, it's a fundamental problem for FRBs, because as they propagate through the plasma, you want to know the plasma response to the wave. And you've got to solve this problem. Okay, so I've been, I had some fun for some months. I think I solved it now. So the question, one you could ask here, so the fluid crosses the pulse in the time scale, right? And first question you could ask, okay, if you are given time much greater than t cross, this is just relative velocity between the plasma, which is pushed to some beta velocity, and the pulse itself, the electromagnetic wave that goes with c. So this is relative velocity. And this is how long it takes for the plasma to cross the pulse and exit behind it. Okay? So if you wait long enough, maybe you would expect a steady state. It's front that propagates in a steady regime. And it turns out, well, the spoiler here that no. It turns out that not, surprisingly, counterintuitively. So one has to solve a time-dependent problem. Okay, I'm not going to explain this technical problem deal. Let me just tell you the question, the method, the keys, and the result. Okay? Question is the following. What is you are given this wave, it's propagating through a background. You want to know the compression factor of the plasma in the wave. Okay, that's the question. And the speed, the corresponding speed of the wave, they're related. Method. The method is just you use, of course, energy. What else would you use in physics? You use conservation of energy, momentum, and okay, and another quantity that I emphasize here. So you start with stress energy tensor for the plasma. This is enthalpy, dimensionless. This is magnetization. This is basically thermal energy of the plasma, rest mass energy of the plasma, magnetic energy of the plasma, magnetic field is frozen. And you're talking about just plane parallel problem, wave propagating, this plane parallel packet going through in the frame or where the initial plasma is static. You have some pressure. Okay, this is the stress energy tensor. You also have the stress energy tensor of the wave. And together, the whole thing has to conserve. Okay, energy and momentum has to conserve. Now, what are the keys? I'll give you the keys, and then you might be able to solve it by yourself now. So one thing is a little technical thing, of course. It's better to switch to coordinates t, xi, where xi is given by this, so that the wave remains static in these coordinates. So you want to follow the wave, otherwise it's awkward to solve it. Okay, this is an important thing. You want to know the enthalpy, and the enthalpy is controlled by that process of test particle calculation that I explained in previous slides. Okay, it's just like cross-section for Thomson scattering. If you want to know Thomson scattering, you can calculate it in the rest frame of the fluid. And same thing here. So you can calculate this W, and it's related, in the case of regular heating regime, it's just related to A0. And an important key here is the following. Of course, energy is conserved and momentum is conserved. But like I mentioned before, the ratio, the difference between them, wave carries no q. For the wave, energy is equal to c times momentum of the wave. So it cannot possibly give any q to the fluid. The fluid doesn't get any q, okay? And that's the conservation law that you should use. Not energy and not momentum separately, but this q. Then equations can be solved much easier numerically, but you can also solve the problem analytically. Not as simple as for the particle that I explained in the beginning, but still simple enough to find exactly the steady-state solution. The steady-state solution you can find analytically. And Amelia was right. So you do find the compression factor A0 squared over 2 for steady state. The only little addition there is that the time that it takes to relax to that steady state, it's a time-dependent problem. And this time scale is proportional to the background sigma. So for an infinitely magnetized plasma, let's say if you take that limit to play with, it takes infinite time to relax. And that's why in the infinitely magnetized limit, of course, you never push the plasma. Okay. Now, you can also solve it not only analytically, of course, you can solve it numerically. It's the full MHD simulation. And it shows, well, I just chose to show the compression factor. You start with no compression, plasma is at rest, and you launch the front and then this wave FRB into the plasma, and you watch what happens. You can calculate the attractor, the final steady state. You can estimate what's the time scale to relax to that attractor. In this numerical example, this is the background, this is A0. You can calculate this steady state compression is 13, and the simulation beautifully shows how it goes exactly to that. That's the time, how long it takes. Okay, and it does scale with sigma. If you do different simulations with different sigma, it scales nearly with sigma. Good. Now, what's the complete picture? Hopefully, plasma responds to strong radio wave. FRB launches a compression front, which slowly evolves toward the steady state when timescale proportional to sigma. Now, when you have this compression growing as it evolves, you actually switch from the regular heating regime, this regular oscillation wave, to this stochastic regime. Because when you have compression, your omega b is increased, local b is increased. Compression also implies pushing. It goes together with pushing plasma along the wave. So you go to the rest frame of the wave, and there you have Doppler redshift of the wave frequency. So wave frequency goes down, omega b goes up, their ratio goes steeply with compression. And so as you keep pushing and compressing plasma by the wave, you switch quickly to the stochastic acceleration regime, which is much more aggressive in depositing enthalpy into the plasma. It's by a factor of 1,000. Okay, regular heating gives you 1,000 times less, it turns out. Now, once you have this stochastic heating regime, your enthalpy is so big, it's accompanied by radiative losses, and your plasma begins to lose energy to radiation. And as a result, your FRB can be damped, because the energy, of course, ultimately comes at the expense of the original wave, okay, the FRB. So this is when, well, I went quickly through this. But this is the final result when you do these calculations. So I hope I didn't, I checked it multiple times by now. I hope it's all accurate. So this plot shows radius. This is luminosity of your FRB. So if you launch an FRB with that power, let's say 10 to the 43, it propagates from the star. This is the light cylinder. In this example, it's 10 to the 10th, and then it keeps going through the wind. The magnetosphere I discussed before already multiple times, and most of you have seen it. So it's damped there very aggressively. But so if you look at the wind, it turns out that the damping continues into the wind zone. So if you keep following this FRB, you find that here in the near wind zone, there is strong damping. Different points here, different colors indicate the dominant damping mechanism. So here is radiative damping. Most of the energy lost by the FRB goes to radiation emitted by this heated plasma. This is the energy dominated if the FRB losses are dominated by the energy kept by the plasma when radiated. And this is the parameter space where the energy of the FRB is mostly taken to compress the ambient magnetic field. Magnetic field of the wave. So there are the free channels to store energy. You can put it in the MHD plasma, either to particles itself or to compressing the field, or you could lose it to radiative losses. So it's mostly we're talking about radiative losses here. And then if the wave keeps moving here, interestingly, it's trapped. So the FRB actually does not, the plasma is unable to cross the FRB front. It's going to surf here. The electromagnetic wave packet, the radio wave packet. And then here is a regular heating zone, but it's unsteady, okay? It takes time to relax to the steady state, which is longer than the age of the wave packet. And then finally, it comes to the region where the age of the pulse, R over C basically, is greater than the time scale for relaxation to the steady state. And here you have the steady state compression in this steady propagating front. So zero order lesson here, important lesson I think, is that electromagnetic waves, strong waves, are incredibly fragile, okay? They're easily damped, unlike normal waves that propagate through plasma. It's somewhat counterintuitive. So you have very strong wave. It encounters the amount of material in terms of energy density and fields, whatever, which is much weaker than the burst itself by many orders of magnitude, and nevertheless it kills the wave, okay? So that's because the wave is like reckless. It's it's aggressive to the particles. It tries to give it too much energy and tries to compress too much. And even though initially the background is so weak, it like absorbs like a pillow the energy from the wave and momentum from the wave. Okay, now, so what it all means, I repeated this message over the years and again for a few years, that FRB, this damping implies, in addition, there is another important process that was highlighted, what was pointed out and calculated by Goldreich and Lubarsky. There is also suppression by the FRB due to nonlinear coupling of electromagnetic wave to the sea of seed Alphen waves. So this aggressive damping that acts inside the magnetosphere, even in the wind, of course, combined together with the fact that energy of the FRB has to come from the central region, because this is where all the energy sits, implies that energy has to be transported from the inner magnetosphere somehow to outside the light cylinder, and there somehow you have to release FRBs. There's no other way, I think. Okay, so that means that we're talking about explosions. Okay, so the energy has to be carried out to the explosion, and so they don't need to experience this strong damping. And now the emission mechanism, just quickly, kilohertz. Okay, so what could possibly meet FRBs? Since I have to go quickly through this part because I think I've lost some 7 minutes at the beginning. So let me just say there are 2 types of models which I think are viable and relatively well defined. So one is what Yuri Lubarsky in particular has been proposing in a few papers. And the idea is the following. You have some structure which is pre-existing. You have a termination shock of the pulse of wind, for example, or in another version, you have a reconnection, a current sheet at the light cylinder, outside the light cylinder of the pulsar, and then you send an electromagnetic pulse through that. So what the pulse does to it, the termination shock, it compresses the plasma a lot, it changes the jump conditions in the shock, and then the shock is amplified so much, and the maser emission that we know should work at magnetized shocks begins to be more active, more powerful, and producing more at the right frequency waves, possibly. So that's one idea. And then current sheet outside the light cylinder, this pulse goes through the current sheet and again boosts its power, amplifies reconnection, and from there you can have electromagnetic waves coming out. The other option is that you have actually the FRB itself, sorry, not FRB, but the electromagnetic pulse, which is typically we're talking about kilohertz pulse, because the pulses come with kilohertz frequencies from the star. This kilohertz pulse of very, like an explosion, if you like, of a piece of electromagnetic field going through the ambient plasma, it should launch a shock, okay? It should itself become a shock, and that shock will keep propagating as an internal shock in the wind around the magnetar and keep producing radio waves. So the Newton star with its magnetic field, I like to think about it as the magnetic field is a little dragon. Well, it's chained to the Newton star, but it's really short-tempered in the sense that if you do a little perturbation on the surface, for example, this perturbation quickly evolves into magnetic explosion. Okay, Yaji gave a talk yesterday showing how this happens, how you can launch an alpha wave, it become linear, how it can become a shock wave. So the important point here is that you have a lot of power originally in principle available in the system, like magnetic energy of the neutron star divided by light crossing time of the system. That's the most optimistic estimate for the energy you can get out, for the power you can get out from the system. If you have a smaller perturbation, okay, the power you can get is suppressed by delta B over B squared, but it's still a huge power. Okay, I'll skip the educational slides, okay? So one thing to note here is that relativistic MHD is so different from non-relativistic MHD simply because electric field in MHD is approximately roughly V over C times B. So in non-relativistic MHD, electric field is always small. You can never have E squared approaching B squared. But for relativistic MHD, you can have it. And actually it does happen. And it's been demonstrated by the peak simulation, first by Alex Chen. It was demonstrated in my MHD calculation. And recently there was another peak detailed analysis in analytic how this happens. So what happens? When you launch a compressive perturbation, which is initially small in amplitude, then it evolves into a shock, which is a surprising result. Because years and decades, people thought that magnetized media don't like to be shocked. If you have magnetic pressure, you don't easily develop a shock. This argument came up multiple times in GRBs, for example. If the jet is magnetized, you don't have a reverse shock. Okay, so in fact, what we now realize, like since a few years ago, that MHD fluids actually do develop shocks, and these shocks are incredibly strong. So the Lorentz factor of plasma developed in these shocks scales with sigma. And because sigma is so large for the magnetosphere of a neutron star, it means that shocks can have Lorentz factors like billions. These are the shocks, the strongest shocks in the universe. And the MHD solution for this, okay, you start with little perturbation, you have spherical wave expanding, this is electromagnetic packet. If you zoom in, suppose you have a sine wave there, it's just expanding with the speed of light. Once the wave reaches the condition where E squared touches B squared, which is inevitably happens there at well-defined radius, about 10 to the 8 centimeters, then what happens is that the full MHD solution shows that the MHD wave, you begin to think about this electromagnetic wave as an MHD wave, where the plasma becomes so heavy because it is pushed to high Lorentz factor, and show it in a second. And as a result, the wave loses its energy. You shave off the excess, this offending part of the wave where E squared would exceed B squared if you don't shave it off. So as the wave goes past this characteristic radius of 10 to the 8 centimeters, it keeps losing eventually half of its energy. Okay, of course, this energy is eventually radiated. So the important part here, these are not just shocks, these are radiative shocks, because they push plasma to very high energies, and then it loses its energy. This is again, it's exact solution in MHD, but it's very simple. This is the plateau at some radius, 1.1 times that characteristic radius. And so what do you have on this plot? On this plateau, you have just a linear accelerator, and Lorentz factor that you reach, as you can see in this example simulation, you reach 10 to the 7th. Analytical Odester relation for the value of this Lorentz factor is just proportional to the sigma background, magnetization parameter of the background. This is radius, this is width of the plateau, which is a order of like wavelength, if you like. It's like half a fraction of the wavelength of this kilohertz wave. Okay, now the new part here is that, well, I keep talking about for past year, I think some of you have seen, I mean, I've been saying that this, in a few meetings, that this wave it should emit radio waves, but I didn't publish anything yet because I will soon, because it's a little complicated problem. Here is the complication. So it's well known, these magnetized shocks. So of course, at the end of this plateau, you have the shock. So here there is a shock. You don't see it as a discontinuity in E, but there is a huge discontinuity in the Lorentz factor of the plasma. So it stops essentially. But like you can think of it's kind of steepening and forming a shock. Okay, now these magnetized shocks are known to produce precursors, what we call, because there is Larmor rotation of particles in the shock, and they. I'll show. I have a slide on that. And so they emit radio wave. When you want to calculate what's happening there, if you want to analyze, of course, what the shock emits depends on the upstream that comes to it, and it's Lorentz factor. But because this upstream is moving through that same radio wave that is emitted by the shock, it is decelerated, it's pre-decelerated. Okay, so you need to solve this problem self-consistently if you want to predict the radio signal from the shock. And then you come again to that same basic fundamental problem, I think, in this field. You want to understand how this radio wave interacts with plasma, but in this case, the plasma is streaming toward the shock with very high Lorentz factor. Well, you can switch the frames, and now you're sitting in the rest frame of the plasma, so you blue shift this wave a lot, but you can still solve it. And so here is, okay, this is the standard slide that reminds you that the shock is basically mediated by Larmor rotation, and this Larmor rotation is essentially, you can think of it roughly as a maser. I'm not sure if it's the best name for it, but anyway, so you can think of it as a maser. It's like a ring in the velocity space, and there are several papers demonstrating in detail what's the frequency of that emission. It's basically Larmor frequency, and how much power comes out in this precursor emission. Okay, so that's the emission that interacts. It is sent into the upstream, And now the upstream is oscillating in this wave, and it's radiating energy, and is decelerated very much. So that's why in the previous slide I showed that the Lorentz factor here, it initially grows along the plateau, and then boom, it goes here. So this is the deceleration process that changes the jump conditions and the radio emission from the wave. And OK, so here is the, I'm not going to explain, let's just look at this panel. This is the prediction, this is the result of this calculation, what radio burst you should expect from this monster shock. This is the frequency of that emission, and this is the power of that emission. The red lines are my analytical. I mean, you can derive this analytically if you're obsessed with it like me. I mean, you really want to understand even analytical scaling, to make sure that things are right. So the nice part here, of course, is that you have gigahertz emission, and you have the right power. Now, right power for which system? Not for cosmological FRBs, which are extremely powerful, but only for this FRB, which is relatively weak. It came from the known magnetar, SGR 1935. And if when you do this calculation, and of course, things depend on the primary power in this kilohertz pulse that was there in the first place, coming from the star, that steepened into a shock, produced E squared touched B squared. And then that shock radiates produce radio waves. Then you can calculate the duration of the radio signal that you have. You can calculate the X-ray power that should accompany it, because the plasma behind the shock is heated and produces X-rays. You can calculate the radio power. That is this complicated self-consistent calculation that I just outlined. You can calculate the frequency. So all these four things work out very nicely for this object. So now I'm sort of enthusiastic that maybe for SGR 1935, that's the only magnetar we know for sure producing fast radio bursts, maybe it does that through monster shocks, OK? It's not working for cosmological FRBs, because for cosmological FRBs, you have huge losses, radiative losses, and the efficiency of radio emission from the shock is small. So the summary of this picture is that, OK, you send the shock, there's radius where it first appears. It first appears in the equatorial plane of your background dipole field. Then the zone where you have the shock spreads in latitude. And then you have two things happening in that shock. You have gamma rays, which are reprocessed into electron-positron pairs. This is the emission that comes from the deceleration of the precursor. It turns out to be in the gamma ray band, so easily produce pairs. And there is a radio precursor, which happens to be able to escape the system despite all that damping that I told you before about. Why? Because it's riding inside. Of course, it's riding inside this electromagnetic pulse. And so it's not going through the background magnetosphere. It's not going through the wind that was pre-existing there. It's embedded in that pulse, and then it comes out. OK. And now I'm worried that you might, after talking that for a while, that you might be, depressed, because I haven't shown a single movie. So let me just show quickly a couple of movies, and we'll be done. So the same physics can happen in other systems, not only isolated magnetars, which produce starquakes because of internal stresses that develop there due to magnetic fields evolving, but also in more extreme systems, in particular in mergers. This is the topic which is very interesting now, because we have gravitational waves from mergers, and you want to understand electromagnetic counterparts. So with Jens Malman, we worked on pre-merger state. So let me show one nice movie. This is how two magnetospheres, two Newton stars. Well, we went to frame co-rotating with the binary. And so this is real simulation, actually. So you can see how the magnetospheres are rotating and trying maybe to interact with each other. So it turns out that, yes, they interact. This is force-free simulation. When you look at the structure of the magnetic field lines, the color here is the electric current density. These are three sample magnetic field lines. They're rotating, they're attached to the star. And you can see interesting current sheet vertical current sheet between the stars. So we describe in the paper why it's there and how it comes. There's interesting dynamics in this binary, which is somewhat surprising. So let me show the movie how the field lines rotate. So you can see how they open up, close, and then again, I'll play it again. So how the field lines break apart and then come back and again reconnect. That's a new interesting feature. But the reason I'm showing now for this context that I was talking about, you see these waves. These are fast waves. So the magnetospheres talk to each other, and there is some traction. Actually, it comes because of the Kelvin-Helmholtz instability here at the interface. So you can see these vortices that develop in this system. And so even when you have simple aligned rotator, Elias, of course, worked out in detail of different force-free simulations for various inclinations. It turns out when we have even simple aligned system, you have traction. You have coupling between the two magnetospheres, and therefore they excite waves, they send waves into the system. And these waves include alternate waves and fast modes, the compressive waves, that can turn into shocks, and then they will produce fast radio bursts. Because this is very clean system. It's pre-merger. There are two old Newton stars, not much plasma around. So if they happen to be able, it's marginally able to do that. But if it sends shocks, there should be some radio signal before the merger. Okay, and one other thing is when you have a nascent magnetar, which you form by, you cook it basically by having two Newton stars, they merge, and they are very massive. They would collapse, but they're still rotating. Before they lose the angular momentum, they might have some lifetime as a massive Newton star. In some cases, it may be like hour, or even day lifetime, although you do need some fine-tuning there. And then eventually it collapses into a black hole. Now, this object, this formed nascent magnetar, it's not just Newton, it's a magnetar because it has a lot of differential rotation. Certainly, the merger has produced a lot of magnetic fields. It's strongly magnetized. And when it collapses, it basically turns into a black hole. It turns from a magnetic field with, let's say, dipole, for example, into a black hole, which should become a monopole field. So what happens during the collapse, the thing is contracting, pulling the field with it inward, amplifying locally the field, and creating compressive waves because now you have an excess of pressure in this field. And as the field transforms from dipole to eventually monopole, it sends this pillow of pressure, it sends this fast mode, what we call it, it sends compressive waves outward and forms a monster shock. So Elias did simulation, Elias-Moss did simulation of this process, and here you see the shock formation. And the hallmark, of course, in this problem is that this negative radial velocity in the shock, which I didn't explain, but I think Yaji hopefully explained yesterday, that in the shock, and it was shown in Alex's paper in the first place, so you have shock plasma, it's sucked in basically toward the star. So you see with this feature in this thing, and you see in temperature, the heating. Okay, so there is a monster shock that comes from the collapse, and it should form a gamma ray burst. This gamma ray burst also, like a little remark here, that ring down in the black hole is imprinted on this outflow. It goes behind that shock. And so it's a gamma ray burst that maybe should be oscillating and with the frequency that knows about the ring down frequency of the black hole, which is cool. And this is new paper. This is beautiful work done by Yoon-Soo Kim, who's a PhD student at Caltech, I think now moving to Princeton. This is merger of black hole and Newton star. The black hole just follows Newton star in this binary. But if the Newton star is magnetized, on the ways it follows it, it perturbs it. And as it perturbs it, it sends alpha waves into the magnetosphere. This is before the merger. This is the Newton star. This is the black hole. There is some magnetosphere around the Newton star. And as the Newton star is being sucked into the black hole, of course, there is deformation of the magnetic field of the Newton star. And this sends compressive waves. And you again form a shock, okay? And this shock is interesting. Well, it's not shown here. It will form later. You can check out the paper. This shock can, again, produce a fast radio burst followed by gamma ray emission, GRB, because that heating in the shock and what follows produces electromagnetic hot outflow, which produces gamma rays. And I'm done. I think it's just one slide that shows what happens after the black hole swallows. It swallows this magnetic moment. If this magnetic moment is oblique and the black hole is rotating, so this magnetic moment will create, it will form a monopole because black hole likes field to be monopole. So you have an inclined monopole which is rotating. and you have pulsar-like state, you have a GRB, which is pulsar-like GRB, because the outflow will be modulated from that system. It's a hot magnetized outflow, Poynting flux, modulated because the magnetic moment is inclined to the rotation axis. And in the simulation, we see beautifully this pulsar state. Okay, that's my summary. So extreme electromagnetism is so different from normal electromagnetism. Instead of Thomson scattering, you have huge particle acceleration, huge cross sections, okay? Instead of normal radiation pressure, you have acceleration by radiation wave field, which deposit momentum directly into the plasma. You have strong compression front that comes from FRBs, okay? MHD waves that we know and love in non-relativistic MHD, okay? They become very different in relativistic MHD because E squared can approach B squared, and then it becomes very dissipative system. And one surprising outcome of this is that you easily create, and actually inevitably create, shocks, mostly radiative shocks in these systems with huge Lorentz factors. Basic lesson from there, extreme fields are very, very vulnerable. Okay, so it's not easy if their life is intense but hard because they're easily destroyed. Okay, now that means for FRBs that they can easily be damped because they are these ultra-strong electromagnetic waves propagating. You know, you don't want to emit them, release them with radii smaller than 10 to 11 centimeters. And finally, similar processes do happen around mergers, and then hopefully produce some signals that could be observable. Thank you.
Thank you, Andrei.